Good morning, everybody. Maybe good afternoon for some of you. I want to, first of all, give a couple of announcements about wrapping up this unit on Chapter 36 and 37. The quiz will be tomorrow, Friday, and it's 5 questions, 5 points, in other words, 1 point per question. Not a super hard quiz as long as you're doing the reading and things like that. But so that's tomorrow. You will also have a transformer article to read and to write a summary, 2 paragraphs, something like that. That assignment will be on tomorrow as well. It won't be due tomorrow, but it'll probably be due on Monday. I'll decide that. But so tomorrow's a quiz, and a transformer article will be given. A couple of you did the transformer article a couple weeks back because it was posted and I had inadvertently put it in the wrong spot. So you could either just submit and just say, I'm one of the ones that turned it in earlier. I think I know who you are, but just to clarify and make sure I get it graded. Okay, so in Chapter 37, what you're reading today, it started a little bit with yesterday's crash course video, but it's on induction, electromagnetic induction. And it's packed with practical, everyday life type stuff. So it's a really important chapter for you to read. I'm not assigning the whole chapter, but so it starts out with electromagnetic induction. And as we learned yesterday, current going through a wire creates a magnetic field. Well, if you take and have an interaction between those two, if you pass a wire, just a wire, not even a current carrying wire, a wire through a magnetic field, that wire will generate in that wire current will be generated. In the intro to the chapter, there's a little intro paragraph which most people probably skip, but it talks about Michael Faraday and Joseph Henry, 2 scientists the same year came up with that finding, just passing a wire through a magnetic field and it produced electricity. Well, that's called electromagnetic induction, and the ramifications of that are enormous. There's applications to electric motors and electric generators and countless things. So Michael Faraday then goes on a little bit later and talks about, or he comes up with the principle that if you have a closed loop of wire, so you put wire in a loop, and if you change the magnetic field in that loop by taking a magnet, passing a magnet through it, etc., I guess I can draw that. You have a loop of wire like this. Sorry. You have a loop of wire, coil of wire like this, bunch of loops on it, right? And you take a magnet, and you pass a magnet in and out of that closed loop of wire, you're going to produce electricity. So you could hook this up to an ammeter, and you're going to get electricity generated. No batteries, no plug-in, no nothing. You just pass that magnet through that loop of wire. So when you change a loop of wire, or change a magnetic field in that loop of wire, current is produced. So that's called Faradays Law. Changing the magnetic field in a loop of wire creates a small amount of current, creates a voltage which produces a current. So there's some applications to that well, there are a lot of applications to that, but let me give you a couple. I've attached to today's outline a couple of photos of what's called smart lights. Smart lights are the traffic signal lights that, like, say you go into coming up to a stoplight and you get into the left turn lane, and somehow that traffic signal knows that you're parked in that left turn lane and you need a green arrow so that you can make a safe turn, right? How does that traffic light know that you are there? And some people say, well, there's weight scale underneath it, or there's rubber hoses, or there's a video camera, and there aren't. What they have done is they have placed in the pavement, in the tar, they've placed closed loops of wire. And there's a magnetic field going through that called the Earth's magnetic field. So then you come over it with an iron car, a metal car, drive over it, and you alter that magnetic field in that loop of wire that's embedded in the pavement. And when you change the magnetic field in a loop of wire, like we just showed right here, right? You create a current or a voltage. And that small voltage that's produced is enough to trigger that light to say, okay, there's somebody waiting for a left-hand turn. We can start the timing mechanism to give them a green arrow. Okay? So those photos, there's one taken on my way to work a couple years ago. They repaved Dell Road south of County Road or Highway 5. That stoplight right there. It's a busy stoplight. And as I was driving to work, I noticed that they had laid in there coils of wire, and you could see the fresh tar in the shape of a rectangle where that loop of wire was. It doesn't have to be a circle, okay? And there are several of them. There's another one of showing the construction of the roadway is all torn up, and I was driving and I pulled off, and I went and ran to the construction worker and I said, "Do you mind if I take a picture of your smart lights for my class?" And he didn't know they were called smart lights, but he said, "Sure, I don't care." So I took pictures of them, and it shows the cutout part of the road. It shows the loop of wire sitting in the background. It shows a trench going over to the ditch. It shows a trench in the ditch that would go to the power pole, the light pole, and the wires would go up there, and that's where it would wire up to that timing mechanism. So I thought that was pretty cool. And I'm going to offer something to the first 10 of you that witness and can see that somewhere while you're driving around. And I'll give you a week or whatever, I'll decide later, but to take a picture of something like that. If you've ever come across that at an intersection, obviously do it when you're parked or get off and come back to the stoplight and take a picture of it. Don't do it while you're driving, obviously. But for the first 10 of you that can see that, take a picture of it in real life. A smart light, you can see the tar. Generally, they'll come by in a next month or 2 months or so, and they'll cover the whole roadway with tar, and you won't see it anymore. But if you can see that, I will give you 5 free test questions. So 5 points in your test category. So like Friday's quiz, you'd get 100%. You wouldn't even have to take it. So which would not be smart because you can get free points. But so anyways, think about that if you can witness that. All right, so that's Faraday's Law. Another really good application of that is talked about in your textbook as well. When you go to an airport or anywhere there is a metal detector, you go through that little stand, right, like this, and there's a little platform here. Well, what this is a loop of wire. And if you change the magnetic field of that loop of wire by walking through it with something metal on you, like you forgot your keys in your pocket, right? It's going to change the magnetic field, which is going to induce a current, which is going to set off an alarm. So it's basically the same principle as doing it in the roadway. It's just with a person that they want to detect to see if they have keys on them or a gun on them or a knife or something like that. So anything that would change the magnetic field would induce that. It has to be metal or a conducting thing, like a pencil wouldn't work. Okay? Let's see. Next, I want you to pay close attention to sections 4, 5, and 6. It does a comparison between an electric motor and electric generator. So the question I'd raise is, if you can use electricity to get a motor to spin, is it possible to just spin the motor and produce electricity on the other end? So instead of, I don't know if I have enough room here, but you start out with electricity, like a battery, and you get this motor, this shaft of this motor to spin, right? Maybe you put a little fan blade on it, like that, okay? And it produces wind. That's an electric motor going that way. can you start with wind with the same device, spin this fan blade, and will you produce electricity on this end? The question is, it's the difference between the motor effect and the generator effect. A motor is just simply starting with electricity and making movement or mechanical work of some sort. And then a generator is going this way, starting with electric or mechanical work, producing this spinning motion and getting electricity on the other end. We know that, or right now they say, oh yeah, we can do that. That's a wind generator. You see them on those big towers, out on the way down to Iowa State or southwestern Minnesota or whatever. There's quite a few of them. That's basically the motor effect and the generator effect. And then lastly, sections 5 and 6 are really important. I'm not going to get into too much with them right now today, but well, actually, I'll do a little bit. I have a couple more minutes on the video. But transformers are basically, let me create a little more space here really quick. Get rid of my... So a transformer is when you have two loops of wire. So you have a coil of wire like this. You have a chunk of metal. And then you have another loop of wire around this. I should go around there actually. So this is called the primary. This is called the secondary. And what happens is you can plug this in to a source, like you plug this into your wall outlet. And this is 120 volts. Okay, you plug it into your regular wall outlet. And over here, let me try something a little different once really quick. So this is just a chunk of metal, kind of a heavy thing, right? So over here I have a whole bunch of wraps of wire called turns or coils of wire. Over here I don't have very many on the secondary. So the ratio of the number of turns over here to the number of turns over here, this is the primary, this is the secondary, will tell you whether or not the voltage goes from here, goes up or goes down. If there's fewer wraps of wire over here, it's called a step down transformer. If there were more turns over here, it would be called a step up transformer. Say, okay, what? I don't get it. So this is your white power plug for your MacBook that you're viewing this on, right? This is that big white plug. You plug it into 120 volts, and out here you might have 12 volts. That's a step down transformer. The ratio is 10 to 1, right? 120 to 12. So that means there's 10 times more wraps on the primary than there are on the secondary. Okay, you get that? Now, if we want to go the other way, if we want to step it up, then we would have the primary over here and the secondary over here. We would start out plugging it into something here, wrap it more times over here, and get a step-up transformer. Step-up transformers are used at the power plant. So like in Monticello nuclear power plant, they would use step-up transformers because, as you'll read in the article tomorrow, power transmission or sending electricity long distances is not very efficient at low voltage. That may be 1,000 volts. That's pretty low voltage. But so they'll send it at 500,000 volts or so, and they'll send it, long distance, from Monticello to here, to Eden Prairie, but then you have this huge high voltage coming into your neighborhood. Then they step it down again at these substations. There's one off of there's kind of by Bent Creek Golf Course, that little industrial park back there. But then they'll step it down even again in your neighborhood. There's those little gray boxes, like say every third house or so, or sometimes they're cylinders, gray or green or whatever, that kind of blend in. People put plants around them. Those are step down transformers again to step it down to the 120 to 240 volts for your home.